Our next topic is beam width. An antenna's beam width is usually understood to mean the half power beam width. The peak radiation intensity is found and then the point on either side of the peak which represents half the power of the peak intensity are located. The angular distance between the half power points is defined as the beam width. Half the power expressed in decibels is -3 decibel. So the half power beam width is sometimes referred to as the 3 decibel beam width. Both horizontal and vertical beam widths are usually considered. Assuming that most of the radiated power is not divided into side lobes, then the directive gain is inversely proportional to the beam width. As the beam width decreases, the directive gain increases. Next is side lobes. No antenna is able to radiate all the energy in one preferred direction. Some is inevitably radiated in other directions. The peaks are referred to as side lobes, commonly specified in decibel down from the main lobe. Next topic is nulls. In an antenna radiation pattern, a null is a zone in which the effective radiated power is at a minimum. A null often has a narrow directivity angle compared to that of the main beam. Thus, the null is useful for several purposes, such as suppression of interfering signals in a given direction. Our next topic is polarization. Polarization is defined as the orientation of the electric field of an electromagnetic wave. Polarization is in general described by an ellipse. Two special cases of elliptical polarization are linear polarization and circular polarization. The initial polarization of a radio wave is determined by the antenna. With linear polarization, the electric field vector stays in the same plane all the time. Vertically polarized radiation is somewhat less affected by reflections over the transmission path. Omnidirectional antennas always have vertical polarization. With horizontal polarization, such reflections cause variation in received signal strength. Horizontal antennas are less likely to pick up man-made interference, which ordinarily is vertically polarized. In circular polarization, the electric field vector appears to be rotating with circular motion about the direction of propagation, making one full turn for each RF cycle. This rotation may be right hand or left hand. Choice of polarization is one of the design choices available to the RF system designer. Next topic is polarization mismatch. In order to transfer maximum power between a transmit and a receive antenna, both antenna must have the same spatial orientation, the same polarization sense and the same axial ratio. When the antennas are not aligned or do not have the same polarization, there will be a reduction in power transfer between two antennas. This reduction in power transfer will reduce the overall system efficiency and performance. When the transmit and receive antenna are both linearly polarized, physical antennas misalignment will result in a polarization mismatch loss, which can be determined using the following formula. Polarization mismatch loss in decibels is equal to 20 log cos theta, where theta is the misalignment angle between the two antennas. For 15 degrees, we have a loss of 0.3 decibel. For 30 degrees, we have 1.25 decibel. For 45 degrees, we have 3 decibel. And for 90 degrees, we have infinite loss. The actual mismatch loss between a circularly polarized antenna and a linearly polarized antenna will vary depending upon the axial ratio of the circularly polarized antenna. If polarizations are coincident, no attenuation occurs due to coupling mismatch between fields and antenna, while if they are not, then the communication can't even take place. Our next topic is front to back ratio. It is useful to know the front to back ratio, that is the ratio of maximum directivity of an antenna to its directivity in the rearward direction. For example, when the principal plane pattern is plotted on the relative decibel scale, the front to back ratio is the difference in decibel between the level of the maximum radiation and the level of radiation in the direction 180 degrees. Our next topic is antenna factor. Antenna factor is defined by the ratio of the electromagnetic field received by an antenna to the voltage produced at the output terminal of the antenna. Its formula is AF is equal to E divided by V. Antenna factor is an important parameter for EMI divided by EMC testing. Electric field strength E is equal to field measurements, where the antenna factor specification defines a relationship between the electric field strength E around the antenna and the voltage induced by the antenna V. Antenna factor is equal to root 377 PD or root 50 PD AE is equal to 2.75 by root AE is equal to 3973 lambda root G. Hope you all understood. Meet you in the next topic.
If you have any queries, please get in touch with us by typing your comment in the comment section. Thank you for watching. Do like and subscribe to our videos. So what are you waiting for? Join us for the course and do subscribe to our YouTube channel and don't forget to press the bell icon. Also, if you like our videos, don't forget to hit the like button and share our videos.